because if the emission lines have a different red shift, if you apply Hubble's law to it, that might mean that they're at a different distance, or else that there's some very dynamic effects going on where the absorption lines are being blown away at very large velocities, and the emission lines are not. And it's very difficult to build reasonable models of what can be happening. But in the model here, it isn't so difficult to produce that sort of thing, because you can have a ring of molecules around something like Saturn's ring or something, or a cloud that could be at a slightly different distance than the central source, and it could, therefore, you would see the dark lines from the light which got absorbed out here have a smaller redshift than the emission lines that is central. And you can build even more complicated models. You could have it be a double star with a very large cloud of electrons, and maybe have a couple of different emission line shifts and a couple of different absorption line shifts. And it's much easier to build models that agree with the observations for quasars if you assume that the red shift is due to the Compton effect rather than the Doppler effect. Well, you might say that the quasars are not the only objects that have a lot of electrons around them. The sun is known to have a lot of electrons around them. And indeed, the sun does have a red shift. And in a paper that I wrote way back in 1968 in Solar Physics, we showed that there's a case in the sun where it also can have observations of a red shift. This is a representation of the sun, and this is presuming that you're at a large distance away. And if you were to look at the sun from down here at the center of the sun, you would look through the electron cloud that's around the sun, the corona of the sun, and you would see a number of electrons. And if you looked at the edge of the sun, looking edge on is like at a sunset through the Earth's atmosphere, you see reddening of the sun there. You would also see, because of the thicker layer of the atmosphere, you would also see a thicker layer of electrons there. And so that if you looked at spots on the sun at the center, you should see more electrons, and whereas if you looked at the limb, fewer electrons rather. If you looked at the limb, you should see more. And you could plot the number of electrons that you see as you go from the center of the sun to the edge, and you'd get a curve that would arise. And it turns out that if you compare the red shift that's observed in the sun, you see that it also follows the same curve, so that the change in wavelength of the spectral lines as you look at from the center of the sun to the limb follows this very nicely. This provides very interesting additional proof that the number of electrons along the line of sight between you and a light source can produce a red shift that is indistinguishable from a Doppler shift. Well, what is this Compton effect anyway? Let's talk a little bit about this so we understand what we're talking about. The Compton effect, well, let's preface this a little bit with a discussion of what happens when light interacts with matter. There's basically only three things that can really happen. If light hits matter, it can do one thing, and that is it could change from light into an electron and a positron. It's called pair production, electron-positron pair formation. It creates an equal amount of matter and antimatter. And this is observed in the laboratory whenever light hits an electron, provided that that energy of that light is equal to the energy of the mass of an electron plus a positron, the rest mass of those. And it has to be at least that high. So electron-positron pair formation is one thing that can happen. And when that happens, it can only happen when in the rest frame of the matter that the light hits, that the energy is very high energy radiation, and that can only happen in the case of gamma rays. So in gamma ray case, you can have electron-positron pair formation. But when you get to longer wavelengths than that, that can no longer happen. Another thing that can happen is a thing called the photoelectric effect. And really what happens in that case is that the the light is absorbed by the matter. And in that absorption, it either heats up the matter or it causes electrons in the atoms or molecules to jump to next higher energy levels, and sometimes creates current that can happen when that effect goes on. And then the third thing that can happen is the Compton effect. And well, in order for the photoelectric effect to happen, the matter has to be in the form of atoms or molecules. It can't be free electrons or subatomic particles of that nature. The third thing that can happen is the Compton effect, and the Compton effect occurs when we have that case where the matter is in the form of free electrons. And what happens in this case is that an incoming bundle of light, quanta of light sometimes called, and normally it's called a photon. The photon will come in and it will strike the electron, and or positron or neutron or any sort of a free particle. And instead of being absorbed in that process, what happens is the electron picks up some energy and the photon bounces off with a little less energy. And this is called the Compton effect, and it's the only effect that can happen when the photon is of longer wavelength than a gamma ray, and when the material that it's interacting with is completely ionized hydrogen or contains only free particles. And so this is the effect that we're talking about here. And thus it's possible to have Hubble's law, which says that the red shift in light is proportional to distance, to be due to the Compton effect if between galaxies there is density, a generally uniform density of free electrons. In other words, if all between galaxies all there are protons and electrons, and there's nothing else there, then the only thing that can happen to the light that comes from distant stars is that it has to bounce off of these protons and electrons and lose wavelength, and go to longer wavelength and lose energy, and in that process produce a redshift that's proportional to the distance of the object. Well, this idea is not unique to me. It's also been thought of by a few other people, and one of whom is Grote-Reber himself. And Grote-Reber has published a monograph here that's called The Endless Boundless Stable Universe. It's the University of Tasmania, occasional paper number 9. And Grote came to the conclusion that the Compton effect was producing a redshift, not the same way I did, which was worrying about quasars, but because of his observations that he was making from his very long wavelength radio telescope. And his observations are very, very unique observations. They're made at wavelengths on the orders of hundreds of meters of wavelength, which is longer wavelengths than anybody has ever made before. In fact, when Grote decided that he wanted to investigate very long wavelength radiation, the initial reaction everybody had was that that was impossible, because the ionosphere would get in the way, and you couldn't look through the ionosphere. The ionosphere would block this incoming radiation. But the more he looked into it, the more he found out that people didn't really understand what was going on with the ionosphere anyway, and that there are places where the ionosphere can become transparent when you're near solar minimum and when you have long night times. And one of these places happened to be Tasmania. And so he was able to make observations with this very large telescope facility that he built in Tasmania. And the results of his observations were very, very remarkable indeed. In his book, he publishes the map of the night sky at 144 meters wavelength.